show you roughly what things look like. So share application. All right, hopefully you can all see there's a slide called How Does It Work? I'm going to talk a little bit about how the analysis works behind the scenes, and then we're going to take a look at the GUI, the graphical way of examining the defects. So one of the things I mentioned is that there is no changes that need to be made to your build in order for us to observe it and run the analyzer. And the way we do that is, however you run your normal build. For example, let's say your build is, make all, or, it's a Python script, or it's a shell script, right, or something, anything. You can prefix it with a little helper command called cov-build. And cov-build, for those of you who are our customers who have seen Prevent, it's the same way we capture source code and compilation information for our static analysis. The depth flag says that we're going to capture all the build dependencies. And what that does is it allows your build to run normally, and with extremely minimal overhead, it's able to watch the build and capture every single thing that your build does. So it sees the commands that are run, processes that are spawned, all the files that are accessed, and what mode they're accessed in, whether they're read, written, whether it's their content that's written or just attributes. And having captured that information into this little database, you can now run a command we call cov-analyze build. And, I say with appropriate options. And what appropriate option means is there are different checkers. And, checkers are different rules that we allow you to enforce. And some of the checkers we've created, and other checkers we allow you to write. And I'll talk to about examples and show you some of these checkers in action. Then you have the results, and you can do two things about the results. One is you can automatically get those results in some format using cov-query build commands. For example, if your build runs automated, you add cov-analyze build, and then cov-query build outputs things to a file that gets saved up. For example, here's the bill of materials for the build that ran at such and such time. Or query, and if there are any new defects, send an email to somebody and notify them to look at something, right? So things can certainly be automated for humans to only be alerted, when there's something significant or different to look at. Or you can use the Build Analyzer GUI, graphical user interface, to examine the issue. And also, especially at first, you might want to tune your configuration. A lot of the checkers kind of depend on you to tell them what is it that you want to allow or what is it that you don't want to allow. So this is the Build Analyzer GUI. And it is, I have it open. I have a number of projects open here. And as you might be able to tell, this is a lot of open source stuff. And I have multiple snapshots. So the idea is that, as you run things over time, you could choose to accumulate snapshots to get some historical information. Most people probably would want to only save the output. And I'm going to clear the search window. I'm going to collapse everything and kind of show you. So we're in the Build Explorer. This is a graphical way to see what it is that your build did. So this is essentially visibility into the build. And we'll talk about, what you can drill into. And you can kind of see, these are all the things you can do, right? You can get some visibility, enforce some rules. So the process tree says, hey, make was the command I ran to kick off the whole thing. And it called make minus capital C dot all, and then it called make capital C source all. I can expand this. I can kind of keep expanding. And basically everything that we observe the build to, to be executing is in here. Quite a lot of stuff. Hey, you know what I'm thinking? This is making documentation. Maybe that's not that interesting. Maybe source is more interesting. So sure enough here, we CD into source, and you can see here's all the compilations. For each command, you see the working directory that the build process was in, the exact full command that was run, And down here you'll see build defects. We're going to get back to these in just a moment. One thing I want to show you is the Performance Analysis tab gives you the exact same view. But in addition, you can see you can kind of drag things around quite a bit. I had to change my resolution so you guys could see things on your monitors. But you can see the freeze command, we're actually showing, you know, the total time, and in this view you don't see the fractions of seconds, so 0 seconds means it took less than a full second. Number of files that were read and number of files that were written. And down here you can see that we list the files that were accessed, and you can filter this out: file content, attributes, directory content, directory attributes. Here are the files that were written. I have chosen in my preferences to have things that are in temp directory to be kind of in a gray font, because I'm less interested in those. And I've also asked for certain system directories to be in a red font. So anything in /bin, /user bin, you know, I want it to jump out at me. These are all options that you can tweak with yourselves. And I also, for example, could filter out and say, you know what, I don't want to see directories. I just want to see files where file content or file attributes were read, and I can do the same thing here for written. Over on the right, you can see some of the details of a particular command. The percentage of total time, for example, that it took. And that brings us to a slightly different view we call hotspots. Hotspots, unlike the process tree where things are in the order that they executed in, are where you can sort things. You can sort them by default. You can see they're sorted by self-time. Now, self-time versus total time. Self-time is how long the command itself took. Total time is how long the command took from the time it started till the time it ended, including the time it spent waiting for other commands to complete. So if you look here, you can see that GCC is actually a command that waited at some point for CC1, which is kind of like a preprocessor, and for AS, which is kind of like an assembler, to complete. So there was some sort of a preprocessing, translating, and assembling, which were all rolled up to the parent, which is GCC. And, you know, in this case, for example, you know, you can see that AS had self-time percentage, which was, you know, much lower than CC1. Total time is the sum of them. And it's definitely more interesting on really large, big, bulky builds where things take minutes, if not hours, where you can then see kind of how much time does the particular command take versus how much it's just waiting for things under it to complete. Getting back to hotspots, and notice it remembered where my cursor was on, you can sort things and you can kind of see, you know, what is taking the longest amount of time in my build. One of the ways that this is valuable is you want to make sure when trying to optimize or speeding up your builds that, you know, you're not spending time speeding up by a factor of 10, something that only takes a tiny fraction of your total build time. So sometimes here you'll see things taking considerably longer. Much more common, you'll see a bunch of things that take about the same amount of time. So for example, you might look at this and say, well, it kind of looks like I'm spending pretty much all my time compiling things. Is there any way that I can achieve an optimization to my compilation time? Because if I can figure that out, well, that'll speed up each one of my compilations. If through this view you determine that pretty much there are no big bottlenecks to your build, it's just overall there's a lot of things that need to be run, you can examine relative dependencies of things and decide that, hey, maybe the best way is to actually parallelize these things. There's nothing that maybe can be done to make them faster, but hey, maybe if we run them in parallel, multiple CPUs, for example, you know, then, you know, we'll be done faster. We won't have to wait as long. One other thing I wanted to show you is over on the right, you kind of have a trace for each command